reading. It's been such amazing day that as a continue from last dimension check of these two camshafts for their wear pattern within that grooves. As we can see, this one has the obvious wear inside the groove caused by wearing down this thrust plate. And this one, being an older one, does not appear to have any sign of wear inside. And we check all the dimensions last time, collect some data, and now is the time to find out what is the reason, what causes this wear. And take a look and see if we can figure out a solution to improve or solve this problem. Now, in order to check the hardness and see if they're being correctly heat treated, we need a Rockwell tester for a hardness tester. And that's such a funny story. And I was trying to purchase one off eBay, and I realized the seller is local. So I emailed the seller and asking if I can just directly purchase from him without paying the eBay fee. Of course, everybody's happy about that. So I stopped by earlier today, and it turns out everybody knows each other, and it's a small group. These guys are car guys, motorcycle guys as well. Such a cool dude. His name is Patrick Donovan, the rock bud, and as well as his brother and other colleagues. This is such a cool group of guys. And so we start talking, and they understand what I'm trying to do. And they said, oh, if you're just going to use that once, man, you don't have to purchase it. You're welcome to borrow one and to have the result. And he said, you know what? As a matter of fact, here's another better choice for you. So he walked me to the back of the room and got this one, a better ultrasonic type of Rockwell tester from GE. Expensive stuff, good stuff. And so I already pre-calibrated. It's very simple. You just put on a calibration block and just light contact, and you will have the reading. So far is a 61.2, although that calibration block is supposed to be 56.5 under HRC, Rockwell C, but it's not very critical for the absolute value for this time. So as we're just trying to do the comparison between these two camshafts and see what's the relative value, what's the delta between these readings. So before I do that, I was just trying to test something else, just to get familiar with the probe, with the machine. So we already checked on the calibration block. It's in the 60s. Now let me check this dolly. The dolly is slightly softer than that, but it's around 50. It's around 50 about this shear. Oh, the shear is actually pretty good. It's around 60s. So the shear is around 60s. Snap-on. Beloved snap-on. See. Good stuff. 60 plus, 66, 64, and snap-on wrench. Okay, it's close to 60. Very well. Now, when I was playing with it earlier, I found something very interesting. So, as we all know, the file, when you manufacture the file, the final step is to heat treat and harden the actual cutting area. So if I check the hardness around the handle, we can see it's a 20s. In fact, the low 20s. Well, we'll say 20s, right? Okay. However, if I move to where close to the cutting area. Look at that, extremely hard. In fact, really, really hard as they're being heat treated, quenched for harness for all the cutting teeth. All right, so enough about the play. Let's do some real testing between these two camshafts. Let me get things a little closer so that we can have a reading. Now let's, I will say, let's check this journal first, since they're where the wear is at. Let me check the new one, the problematic one. Vertical 52. Okay, let me rotate that a little bit. It has to be vertical. 56.9. 57, pretty consistent. 55.9, so around 56, around 56. Now let's check the non-weared one. Oh, 54.8. This is a not precise reading for that one. Let's keep doing. Okay, 56.9. So far, the value is actually very close. 57, 61.5. Check on this side. 58.7. Here on this side. Interesting. Wow. So that it's actually a little softer on the outside edge. 51.4. 44.4. 46.6. Now this one on the outside, 53.1. 63.6. I'm not sure about that. Oh, off the limit. That was an invalid rating. 44.8. 58. So it's generally 50.2, 51.2. And the other one is 53.5. I have a feeling it might cost 57.2 now. Interesting. Well, I was carrying a hope that this one actually has a lower reading, but so far it seems everything's pretty consistent. I mean, very similar. Okay, so as the main journal part are almost identical, and these two, although they're kind of back and forth, but overall is kind of similar. Now let's see if we can try to measure the cam lobe. As we can see, the old one doesn't show any sign of wear, but the new one we see wear patterns on each lobe, which means if all the running conditions are the same, then there's something wrong with the new one. Let's see the new one made by Kent. 59.6, 63, 61.5, 58.3. So let's see the other one, the old one, Crane. 62.5, 65.4, 61.5. Oh, I guess that's an invalid reading. 65.4. 52. I don't think that's correct. Why is going back and forth? That looks more about it. Yeah, that looks more like it. Okay, so feels to me that journals are the inconsistent. I don't understand why, but it seems like they are very close in hardness as well. So let's take a look at this thrust plate. 69.7, 68.8, 659, off limit, 681, off limit, 671. So let me flip it. It looks like it's at the high 60s, same high 60s. That one's 62, high 60s, 61, high 60s. Interesting. Okay, seems like I have to really guarantee the probe goes down vertically. Plus this surface is a little bit rough due to the wear. But what I find out in general, it is, see, if I go with the non-worn part, high 60s, well, low 60s, mid 60s, high 60s. Now let's go to the worn part, high 50s, mid 60s, 60s, low 60s. So it's very interesting to see that the warm part may actually get generating sufficient heat to anneal that section to actually make the worn surface get softer. And that's definitely not a good thing, because it's still constantly contacting surfaces. The softer it is, the more wear it will has. The more wear it has, the higher the temperature, and the higher the temperature, the softer it gets. So it's a very bad cycle. Now, so I think I can have a conclusion that the hardness of these two camshafts are very much alike. So besides from the different in the material hardness, what else could affect the different level of wear? Now, I would guess maybe the different components, different alloy, it could possibly change the coefficient of friction, right? So we were actually talking about that, and this dude, Patrick G's, he said, "Oh yeah, there's another thing you should use." He grabbed me this gun, Jesus, and it has the radiation sign there. It has this flipper screen, very fancy. He said, "Oh yeah, just 20 grand machinery. Let's make sure bring it back." This thing is radioactive. It's radioactive. So made by GE. It will emit X-ray, and you shoot on the surface, and it will tells you what component that surface is. I mean, literally. So you can see the element content. So let's try one at the calibration block, and we pull the trigger, and it's analyzing, and it tells you has a chrome in there, majority 97.22 of iron, and quite frankly speaking, I don't know what LEC means. So just to make sure it is not lying, I grab a piece of aluminum. It's kind of dirty, but let's see if we can read anything off that. I'm pulling the trigger. Oh, look at that. It's very fast. Even with that dirty surface, tells you 99.44% of aluminum and a slight iron content on the surface, and I'm pretty sure that's from that's not alloy. That's probably from the grinding dust. All right. So either way, boy, Patrick, you guys are kick-ass. Thank you so much. It's being so generous to let me borrow the tools. You guys rock the world. Just for you, let me check another one. Let's check this block. Pulling the trigger. All right, so there's a little more content. It has a molybdenum in there, I believe. So majority is still 96% of iron. All right, so enough horseplay. Let's start testing. So I will start from this surface. I will try to be as close and precise as possible and see what we can do. And I'll make sure I'm not touching the screen, because, all right, here we go. I believe it's still reading. Okay. So, okay. 7.43. Okay, let's rest this baby down here for a second, and then let's write this down. Oh boy, I pressed the trigger. So yeah, let's do that again, and it'll be a great opportunity to see if it's still same. Well, that was fast. All right, so let's see. 0.277. I don't really know how to pronounce that. I know the Chinese name. 0.703. Iron. Ooh, start leaking. Let me get another marker. Will be 97.41. Molybdenum 0.033. We all know this is a LEC 1.29. I don't know what that is, but yeah, LEC is 1.29. Now, let's check the other cam, same place. Pulling the trigger. Okay, not sure. It seems like it's still detecting, because it's not such a great position. Okay, let me write the number down. This one would be iron is 96.78. Chrome, whoa, 0.824. Wonder why. 0.0853. 1 point. It has copper in there. No, that's gold. No, that's copper. 1 point. Well, molybdenum 0.0. Oh, 0.466. Wow. Let me double check on the far side, because by the element content, the old one should be much harder than the alloy than the new one. Let's check the old one again. There we go. Okay. Let's see. Not sure if it stopped or not. Okay, that will be 96.98, very close in iron. And 这个锰, I don't know how to speak in English. It's 0.825 or 815. Yes, very close. Chrome 0.603, close. Molybdenum 0.478, very close. Okay, so it's actually quite close than our previous test result. Now let's go to the newer Kent one, probably made in England. All right, pulling the trigger. Okay, immediately we see higher content of iron. All right, so it is pretty obvious that let me compare 97.18, very close. 0.582. Oh, Chrome looks different this time. 0.582. Okay, but still it's lower than the other one. 0.606. Lower than last time. Copper, we didn't capture any copper last time. Molybdenum 0.030. Alrighty. Well, thanks to the machine, thanks to Patrick, and thanks to GP Technical. Boy, I think the problem is actually from the different alloy. And the actual problem is not from the hardness, as they are very close to each other, but rather from the different alloy content, different type of alloys, and thus cause a different coefficient of friction. So, and of course, just the abrasion resistance. And I believe I need to review my chemical and metallurgy class, but I believe with higher content of chromium and molybdenum on the older one, very noticeably higher than the new one, it probably will be making the mistake, making the difference. You know what? Let's check this thrust plate just for reference. Okay, pretty straightforward. It's just iron, and I need to find out what's the proper English name for the MN. I know that Chinese name, but yeah, so technically this one without the chrome and molybdenum in there should be less wear resistant than the camshaft itself. Interesting, very interesting. We can clearly see the wear here. Let me check the journal for one more time, just for documentation purposes. This journals, everything I've been testing has been Scotch-Brite and acetone. So the new one, the problematic one, we're reading of 97-ish iron, and I don't know where that titanium has come from. Old one, the better one. Wow, we actually pick up zinc there as well. The zinc, I would expect is from the sacrificial material from the oil. so it's accumulating to where the cam lobe is rubbing on the rocker pad. Okay, so wow, that's a lot of stuff there. Either way, I believe the conclusion is the hardness are almost identical between those two camshafts, and I will start to study the difference between those two alloys and see if they are the actual reason to create a different level of wear between these two camshafts. Again, I really want to say thank you, appreciate it for Patrick and Jordan and all the fellas from GP Technica, lovely people. And if anybody ever need any high-end precise measuring equipment, they're local, and I didn't even know they're there, and I didn't even know we're all in the same group and the friend, and I found out his wife is my son's teacher. What a small world. But either way, thank you so much, guys. You guys are so lovely. I'm so excited. We're all dedicated to science, and yeah, I'll keep everybody updated. Peace out. Thank you.